You've built this huge following on social media, blowing it up. Is this what you do?
That's what I do. Yes.
So you have thought about what would excite them visually and intellectually. How much of this world is empowered by chemists? Two new elements, when they come together and they make something new, can you predict its properties?
If you're going to rearrange atoms, likely you're going to need to break bonds and then make bonds.
What happens if I put a hunk of sodium in water?
Hydrogen gas is going to be evolved, which is extraordinarily flammable. It's an exothermic reaction, so usually it will ignite and you'll see a flame. Boom.
That's the chemist's way to say it'll blow up.
Boom. Yes.
Okay, I'm doing the experiment tonight.
Do it. You will feel it. You will feel it in your hand.
Tonight.
The experiment gauntlet has been thrown down.
Next time you make anything in your kitchen, just sit and reflect on the fact that none of that would happen without chemistry. This is Star Talk. Neil deGrasse Tyson here, your personal astrophysicist. We got a Cosmic Queries edition coming, all about chemistry. More on that in just a moment. Chuck,
Hey.
how you doing, man?
I'm doing well, man. How you doing?
Okay, who's that sitting next to you?
I got to tell you, only the most awesome chemist ever.
Ever.
Like, if you have anything called social media, then you have seen her conducting demonstrations of chemical reactions and explaining to you the wonderful world of chemistry.
Chemistry, Kate the chemist.
Yes.
Hi.
Welcome.
Hi.
Welcome to Star Talk.
Thank you.
And I need training on how to pronounce your last name. Bieberdorf?
Bieberdorf. Perfect. Yes. Bieberdorf.
Bieberdorf.
So like Justin Bieber and then Dorf. That's what I always say.
No, that's wrong.
The
You
alter
can't have it.
ego of his fan club.
It's that sounds like a fan club.
I'm a Bieberdorf.
Bieberdorf.
I'm a Bieberdorf. Are you a Bieberdorf? I'm a Bieber. I'm a
Oh, I like it.
Yeah, Bieber.
My students call themselves the Bieber dorks. So
Bieber dorks.
Yeah,
Good.
so I'll take
good.
that too.
That's good.
I like it.
that.
That's cool. I like
That's
it.
affectionate.
That's
That's
I'm
affectionate.
a Bieber dork.
So you're not just Kate the chemist
Right.
in your social media. You are associate professor of instruction and science entertainer. That's a thing. I'm glad that's a thing. Why can't that be a thing?
That should be a thing.
You know, and associate professor of chemistry, University of Texas, Austin.
yes, hook 'em horns.
Oh, hook 'em horn. There it is. Okay. So you built this huge following on social media, blowing shit up.
Yeah.
Is this what you do?
That's what I do. Yes.
That is so cool.
Wait, so how does that work on Twitter or in the medium where you don't have a video?
It's difficult for
Okay.
sure. I mean, you can share a video on Twitter
Yes, you
still.
can.
Yeah. But on Twitter, I try to be more academic, right? I highlight articles that I like or science.
Twitter X, excuse me.
Yes,
X.
apologies. Yes, thank
X.
you. But, highlight
Twitter.
good research or hot science in the moment. So it's easy to do that. But I will.
Directing people.
Correct.
Yes.
Yes, exactly. Or highlighting scientists that I like and saying, hey, you should follow this person or this person.
Okay.
But you are right. I mean, Instagram and TikTok are my big ones because it's very easy to get somebody to like you, breathe fire. I mean, that's just fun and visually appealing.
Yes. And so are these people who would not have otherwise been chemistry fans, do you think? And they're attracted to your clever way of bringing it down to earth?
But that's a compliment, so I will take that. But probably, yeah, I mean, honestly, most people hated their chemistry class. I hear that all the time,
among
right?
them, yes.
Both of you? Yeah, and that's terrible for me because it's my favorite thing. It's my absolute favorite thing. And so if I can...
By the way, anyone in your role who's also trying to do that with math has the same story. People hated their math class.
They don't have fire. I at least have fire. I have liquid nitrogen. I have
Right.
tools in my tool belt that I can use to get
Yeah, the math
kids
is
excited about it.
They got nothing.
A calculator? It's not as
They
exciting.
can write pi
Yeah.
to 10 digits. All right. So you have thought about what would excite them
Right.
visually and intellectually.
Well, I was raised by psychologists. All of us agree on William James's theory of emotional memory. And so it's about if you have an emotional response to something, you're more likely to form a memory.
Absolutely.
So in the classroom, I can use fire. Like if I light my hand on fire, now all of a sudden the students are interested. And the research shows I have about 60 seconds to then teach
burn
them why
marks.
that
We're
works.
looking at her hand
Oh,
right
the research shows that
Yes.
rather than your life experience.
Yes, also true.
That would
Yes.
also count as data, for sure.
For sure. Oh, for sure.
So you burning it like an alcohol or something? In
No,
your
so
hand?
you dunk your hand in water first, and
Yes.
so you cover it. Water has a really high specific heat capacity, and so it takes a lot of energy to raise the temperature of the
Yes.
water.
So
So it
that's
acts
an
like
insulating layer.
Exactly. Yes, exactly.
Yes.
So it acts like a lab coat. Then you grab bubbles that have been pumped full of methane. Methane is very flammable.
Mm-hmm.
You hold on to it, you can light the bubbles on fire, and your hand doesn't burn at all, as long as you keep your fingers open. If you close your fingers or you're wearing rings, now you have a problem. But it's totally fine. But now the students are interested.
But just to be clear, methane, such as the gas that comes out of...
Cows. Is that what you're
no.
going to say?
Okay, cow.
Right. Cows. Let's leave it at cows.
Let's leave it at cows.
We'll leave it at cows.
It's a flammable gas.
Right.
So what you've done, at the risk of stating the obvious, is you've taken psychological research to turn yourself into a better chemistry teacher.
Yes, 100%. 100%. Yeah, I mean, the point at the end of the day, my goal is for students to become good scientists. Only 5% of those students become chemistry majors. So I really want them to be educated voters. I want them to
Oh,
be
you mean
able
in your
to,
class?
in my class,
Yes.
yeah, my class. And so I want them to be educated voters. I want them to have quantitative reasoning skills, quantitative thinking skills. And so for me, it's all about building those skills through the lens of chemistry to try to make my students as smart, like the best citizens we possibly can have.
And how about your following? They just want to see stuff blow
Blow up?
More,
Or
yes.
they can become like chemical engineers.
Yes, that's for sure.
You must know because they'll write to you. right?
Yes,
Yeah.
they do.
Yeah. So what do you know?
They like the explosions. They like the really quick, fast things. They do not want me to drone on about the structure of an atom.
But you never know when that will spark the curiosity that leads them to want to know what's behind that explosion.
Yeah, there it is.
You know, my son started off with just chemistry and liked it so much that he's going to school now for biochem.
You didn't tell me
Amazing.
that. You
Yeah,
didn't tell
he's
me
going to be
that.
a biochemist. That's what he tells me he wants to be.
You didn't tell me that.
Yeah.
great
And I
kid.
told him, don't be a biochemist. Own a biochem company.
Not a bad idea.
Let's get some basic chemistry on the table, okay? I can't claim to even know the answer to this myself. What is a chemical reaction?
Ooh, okay. So chemistry in general is the study of energy and matter and how they interact with each other. And so a chemical reaction is when you have a starting material, you do something to it, and you get a brand new product. So like if you're baking a cake, your reactants would be eggs, flour, sugar, chocolate chips, something like that. And then
okay.
you add heat,
You put
right?
chocolate chips in cake?
Yeah.
I don't know. I'm just making
That's
something
a
up.
waste.
Yeah.
Cookie.
Well, maybe you melt it, so it's a chocolate cake.
Okay, good,
Something like that.
good,
There we
good.
go. Okay.
Oh, molten chocolate cake. Okay.
That's good. That's good.
good.
Okay,
I'll
yum.
take
Okay,
that.
so then we have to heat it up, right? So you're going to put it in the oven.
So that's
and
an energy
then-
source
An energy
going
source.
into the cake.
Exactly. And then you're going to take it out and you have a brand new product. So a chemical reaction is you have starting materials, which we call reactants, and then you have a product at the end, which is the goal. That's what you're trying to produce, what you're trying to make, or what you're trying to study.
Okay, so now there are many things you can do that with, but then if you just wait long enough, this thing that you made turns into something else. Like
Like iron turning into rust.
Yes.
so other things can happen even after you're done doing what you're doing.
Oh, yeah.
So they would happen without your intervention.
Correct. So that goes back to being a spontaneous reaction. And so I'm going to jump into some thermodynamics. So pull me back if I go
Love me
too
some
far here.
thermodynamics.
Okay, okay.
Plus, I'm hearing these terms. It's easy to see now why people use the chemistry terms to refer to human relationships.
Right.
We had spontaneous reaction.
Right.
Chemical was in our chemistry.
Yes.
These are your words, not my words.
They are my words.
Right,
Yeah.
right. Astro, we don't have that. Yeah, you got all the words for relationships. Okay. so go
Very,
on.
very fair.
Yeah.
So for a spontaneous reaction, this is a chemical reaction that will happen on its own in isolation. And so usually that's something that's exothermic. So it's going to give off heat as it goes from the reactants to the products. And it's usually something that has an increase in entropy. And so we know the second law of thermodynamics is to increase the entropy of the universe.
Yes.
And so if we have something that's exothermic, meaning it gives off heat, and then it has an increase in entropy, meaning the energy is spread out more so, that's a favorable reaction that would be spontaneous.
That's just the universe just being the universe.
Exactly. And
Without
that's
your intervention.
without my intervention. So that's a reaction that will happen on its own. So they don't even need me to do this.
Okay, so does the formation of diamonds count as happening on its own if that needs pressure and temperature and time?
That's what I was going to say. What are your conditions?
Yeah.
So
Okay.
I would say yes
So
over
I
time.
just can't put a lump of carbon on my table
And
come
wait.
back and wait for it to become a diamond.
Not for us. We will never see that.
Right.
Yes.
No.
But even though I did get a lump of carbon every year for Christmas, but that's okay. I mean, we're not going to get into that right now.
Sorry.
However, but is it really happening on its own, or is the Earth actually providing the conditions necessary to make that reaction happen?
Great point. Absolutely great point. So on Earth, we refer to something as SATP or STP, so standard temperature and pressure.
Okay.
If we're talking about thermodynamics, that would mean we're at 25 degrees Celsius, so 298 Kelvin, and then 1 atmosphere. And so those are the conditions where it would happen on its own
25
naturally.
degrees
Celsius.
Celsius. That's like a little higher than room temperature?
Yeah,
Slightly
it is.
higher?
25 is what we call room temperature.
Oh, I didn't know that.
Yeah, 25 C in chemistry at least. That's how we define that. And so that's probably like, I don't know, 73, 75,
Yeah, it's a
something
little
like
above
that.
72.
Oh, 72. Okay.
It's a little above
73.
72.
That's what I said. Okay, cool.
Yeah.
Okay, and then at 1 atmosphere.
At 1 atmosphere. And
Of
that's
pressure.
of pressure, right. And so that's how our chemical reactions occur here on Earth because those are what our standard conditions are.
So I heard something. Is it beryllium? One of these elements on the periodic table in American charts is listed as a liquid, but in the UK it's listed as a solid.
But that's gallium.
Gallium.
I was like, beryllium.
Excuse me.
It's okay. Sorry.
Her voice was stupid.
No.
Right. So we talk about gallium.
Gallium. I think so.
Gallium. So in the UK, it's listed as a solid because the room temperature in the UK is colder than here,
Wow.
and so it changes state at that point. So the conditions are everything. What you think something is
It's only what it is under those conditions.
Under those conditions.
Exactly.
That's it.
Yes.
Very cool. So one last thing about these exothermic reactions. There's also endothermic, if I remember correctly. So that's exactly what's going on. If you have a sore muscle, you get this pack and you sort of smash it and it becomes warm. There's another pack you can buy, you smash it,
and it becomes
and
cold.
it becomes cold. So people like you has something to do with that.
Oh, thank you. Yes, I'll take credit for that. Absolutely.
Yeah, your people.
My people.
Your people. So you have special chemicals in there, which when combined, forcibly combined, will either absorb energy or emit energy or release energy. And so you have to know what those are in advance, obviously.
Oh yeah, absolutely. And so usually how those things work is there's one pouch that's filled with something, and then there's another pouch in the inside. And so you're breaking the two pouches and allowing for the two things to
The
mix.
membrane between them.
Right, exactly. It's a
Yeah.
really thin membrane, and just with a little bit of force, we can break it.
Okay.
What's neat for endothermic reactions is it's usually a salt that will dissolve in water. That's going to drop the temperature down. It's freezing point depression. And so that's what's going to be very, very cold. And we'll use it if you have an injury.
Right.
Okay.
And that's what they do when you make ice cream. That's why they use salt.
Yes. Oh, yeah.
Exactly.
That's correct.
Yeah.
Well, I think there's a different reason.
Really?
Yeah.
Why?
Yeah.
If you make it by your hands, though, you add a little bit of salt for it so that you can go back and forth. Yeah.
What do you make ice cream in your hands?
You put it in a Ziploc bag, and then you put milk and sugar,
and then
vanilla.
you can put it in a towel, and you put that inside of another bag of ice and salt, and then take the towel and just whip it
Here's what I'm
around.
saying. I'm an ice cream guy
Okay.
from way back.
All right.
I should weigh 100 pounds more, but I exercise just to wear off the
just
ice
enough
cream.
to wear, just so I can eat ice cream.
Got your bucket, and it's filled with ice.
Right.
If you try to make ice cream that way, the cold of the ice is only pulling the heat out of the ice cream at the points where the solids are touching the rotating cylinder. Everywhere else is air. All right. You put salt on the ice melts at that temperature.
Right.
So now the medium is liquid.
And the liquid is now touching
It's-
every single part of the
And it
cylinder,
is
but it is the
way
same
better.
temperature.
At the
It's
same
much
temperature as
colder.
the ice, correct.
Okay, that
And
makes
it's
sense.
way better at sucking the heat out than just solids that it's turning within.
All right. I'll accept that. Cogent argument you have made.
That's all I'm saying.
Which I should have known, because at first I was just like, all right, I finally got this guy.
No.
I'm like, I know for a fact that it's to lower the temperature, but that makes
Yeah.
perfect sense.
Yeah.
Makes
Okay.
perfect sense.
So I would claim that salt and water does not lower the temperature. That's what I'm claiming.
Salt in water will always have freezing point depression. That is a thing. We can measure
Well,
that.
no, I get that.
Yeah.
But if water's at a given temperature and salt is just the salt, I'm going to assert that you put the salt in the water, nothing happens to the temperature. That's what I'm going to claim.
False. Freezing point depression. It will go down. Delta T is equal to negative IKF times the molality.
By how
Mic
much?
drop.
By how much will it go down?
If you put salt in water, it goes down by negative 1.86 degrees Celsius.
Per
Yeah, there has-
It's molality, so it would be moles of solute divided by kilograms of solvent.
And does it matter what kind of salt?
Definitely. Yeah, it has to do with the Van Hoff factor.
Okay.
Yeah.
But at home you just have table salt.
Correct. And so it has a Van Hoff factor of 2.
So will this work for table salt?
Absolutely. Yes. Because when you put sodium chloride in water, it's going to break apart into the
Okay,
ions.
I'm doing the experiment tonight.
Do it. You will feel it. You will feel it in your hand.
I'm doing the experiment.
That is cool, man. I
Tonight.
love
Yes.
it. The experiment gauntlet has been thrown down.
I promise you.
Okay. So how many degrees?
I challenge you,
think I can
sir. Ions at dawn.
2 Celsius max.
get? 2 Celsius.
Max.
Of what volume of salt?
I would make a super saturated solution.
Oh.
Yeah. So take a bunch of water, just dump salt in until you can see it at the bottom.
Yeah.
Stir.
Stir,
And you'll feel it. You will physically
Right,
feel the
right,
temperature go down.
So I got to super saturate it. That's a lot of salt.
Just, but don't do a lot of water. Just do a cup of water and just like you'll feel it.
Well, you have a huge fan base, and they heard you were coming on the show, and we solicited inquiries
Oh,
from them.
exciting.
And what do you got here? I haven't seen them. Have you seen them?
No,
Nope.
we don't let. We
Oh, yeah.
Yes.
Okay. All right. It's a loving.
Yeah,
I
they,
promise.
they only ask things that they're really a great audience
Yeah.
and they're very curious and
Okay.
they ask
And
great
they paid for the privilege to ask a question.
Yes, they are our Patreon members, and so
No, just at per month.
it's $5 a month if you're interested out there and
Which
you
is
want
the
to join
cheapest
Patreon.
membership of anything you would ever
Exactly.
have. What do you
All
have?
right, here we go. This is Samuel Barnett. He says, "Greetings from London, England. Given the properties of molecules don't seem to match the properties of the elements they're made of. Example, water extinguishing fire despite being made of highly flammable oxygen plus hydrogen,
Right.
which we learned that's the big tanks on the rockets that take the space shuttle to space.
Yeah, the orange tank right
On
there.
the orange
visible.
tank, there it
Right,
is.
yeah, uh-huh.
So he says, is there a way to tell how a new molecule will behave ahead of time? Or is it just a case of suck it and see, or
I love that.
I'll say I'll clean it up for him. Trial and error.
Yeah.
yeah. Can
Okay.
you predict two new elements when they come together and they make something new? Can you predict its properties?
Yeah.
We will try to. So the periodic table is organized based on size, but it's also based on chemical properties.
Size meaning size of the nucleus.
Size of the whole atom.
The whole atom.
The whole atom, yeah. So including the electrons. And so when you look at a periodic table, if you go down a column, you would expect for every species in that column to behave similarly. So for example, if you go all the way to the far right on the periodic table, those are your inert gases, your noble gases. All of them have full octet shells, meaning they're not looking for an external valence electron. They're full.
They're happy in and of themselves.
They're satisfied.
There's got to be some psychological. You
Yes,
are
exactly.
content.
You're content.
It's very.
I really like it here. I gotta tell you, this electron shell just suits me perfectly.
I know. I don't need
I
anybody
don't know
else
what
to help.
it is. You know, I'm looking down at my nucleus. I'm just as happy as I can be.
That's it. There it is. The
Perfect.
right hand column personified by Chuck.
Yes.
Okay.
That's perfect. But you would expect everything. So like argon, neon, krypton, all of those gases to behave in a similar way. And so let's say you look at group 5, you've got nitrogen at the top, phosphorus is right underneath it. So you would expect for nitrogen and phosphorus to behave similarly. And that makes sense.
In a reaction, in a chemical reaction.
In a reaction if it's bonded to the same partners. So
Got it.
I would compare NH3 with pH3, and I would expect them to behave similarly, not the exact same way.
NH3, so that would be ammonia.
Ammonia
Yeah.
versus pH3 phosphine. And so we could compare the two of those and expect them to behave similarly. They each have a lone pair. They've got an electron pair available. So,
Interesting. That's
yeah.
a fair answer. I like that.
Oh, totally.
cool.
Yeah, yeah. That's,
You can predict it, but then you test it.
Right. You predict it and then you blow something up. There you
yeah,
go.
but I bet
Safely.
people before you understood the periodic table, there must have been a lot of trial and error.
Of course.
Yeah.
But there still is. There's still
Yeah.
trial and error. You have a guess. You want to use your money the best you possibly can. You only have a limited funding. So you want to put your eggs in the best basket.
Yeah.
So how about now? There's something in AI, I believe it's called offline reinforcement learning. And so what that does is the AI observes a bunch of things similar, and then it makes predictions based on what it's observed. Do you guys use anything like that to figure out?
That's the definition of science. That's what we do.
Duh.
We stare, right? I mean, right? We watch something. We
Right.
try to detect patterns. That's all we learn in
Except
grad
we
school.
don't use AI. We use NI, natural intelligence.
Oh,
Nice.
okay, right on.
Fist bump.
I'm going to say that's a little more rare.
All right, next question. Who do you have?
All right, this is Mike Muhammad Kaki. He says, greetings, Dr. Tyson, Dr. Bieberdorf, and Lord Nice. Mike Kaki here from Berlin, Germany. Can you explain the role of activation energy in a chemical reaction and how it influences the rate of reaction?
I love that.
That's a beautiful question.
What is activation energy?
So activation energy is the minimum energy required for a chemical reaction to occur.
So it's sitting there otherwise happy
Yeah?
until you put energy in it, then it runs away?
Yes, sometimes no. It kind of depends on the conditions and what else is going on in the environment. But in general, if you're going to rearrange atoms, likely you're going to need to break bonds and then make bonds. And so activation energy is that minimum energy required to actually rearrange those atoms.
In whatever way is your intent.
Right, exactly. And so it's based on the collision. And so the orientation of the molecules matters. If you need them to hit head on and then they do like side by side, you might not have the collision.
Wait a minute. You know how the molecules are oriented?
Well, we know that what orientation, what collisions are favorable. And so we know if these two atoms need to interact and form a bond, if you have the molecules slap each other from the other side.
So do molecules have like docking ports, basically?
I'm okay with that.
Yeah, what I'm saying, yes, but how do you configure them to know which docking ports are pointing which way? Aren't they littler than you can see?
Well, sure, but you know that if you have one side of the molecule, like let's say I'm a molecule, and I know that my right hand needs to form a bond with your right hand. If our left hands collide, we're not going to form a bond because those aren't favorable interactions.
But how do you control that?
We can't.
Oh, okay.
No.
That's what spooked me.
Oh, no.
I thought she's up there with tweezers, putting one molecule.
That's the dream. I would love that.
To another. All right.
No, we can't because it's usually in solution or in gas phase. So the collisions are not. Yeah, we can't control that.
Okay.
No, but what has to happen is they have to collide with enough velocity, so kinetic energy, to overcome the potential energy push away. So the
that would count
proton
as an activation energy, the speed.
Correct.
That they collide.
Part of it. It's part of it.
Okay.
All of it. And so you have to have the energy coming in that is stronger than the proton repulsions that are happening between the atoms, and it has to be at the right collision. All of that is kind of looped up into activation energy.
And can you know that in advance, like from equations, or will you measure that?
100%. Yeah. So you would use an Arrhenius law. So it's the natural log of rate 1 over rate 2 is equal to your activation energy divided by R times 1 over T1 minus 1 over T2.
Arrhenius.
Wow, you are good at this.
I had to find it.
This is like way back.
Way back. Yeah.
Arrhenius.
Yeah. And
when was Arrhenius?
Ooh, I don't know. I couldn't give you a year.
Long enough ago that nobody is named Arrhenius. That's how long ago it was. You have never met an Arrhenius in your life.
And Arrhenius doesn't even have a middle or last name. It's just
It's like
Arrhenius.
Cher. I'm Arrhenius.
I love that.
Yeah.
You know what I'm trying to figure out, though, that some reactions are just so favorable or so common. Can you take what you said and I'm lighting a piece of paper on fire, which is a reaction that everybody knows. What would be happening there from what you just explained?
I would say the activation energy was the match.
Yeah.
I'm spitballing here.
Part of it.
But
Just
I'm
saying.
thinking.
Yeah.
I'm just saying.
So if you have a fire, that's a combustion reaction. So you have a
Okay.
source of fuel, you treat it with oxygen, and you produce carbon dioxide and water. And so what you're doing is breaking all of the bonds in the fuel and the oxygen, and you're rearranging it to form carbon dioxide, CO2, and then H2O. And so it's all about literally pulling these species apart, pulling the atoms apart, and then allowing them to rearrange and form a new bond.
And is it, based on what we said moments ago, is it fair to say that whatever's the configuration of the molecules in the paper, the configuration afterwards has lower energy? Because all that energy became
you
in the
release
fire.
the energy.
Right? Is that a fair?
fire.
Did I say that right?
If it's favorable, yes. If it's favorable, you're going from higher energy to lower energy.
Yes.
But if we had to force that, if we were in like extreme conditions to make this happen, then not necessarily. You
Right.
can force things to go higher energy. But
Okay.
usually,
But at
for what
the
you're
cost
saying.
of putting the energy in.
Correct.
Yeah. Okay.
Yes.
Okay. All right,
Exactly.
All right. That was cool, man. Thanks a lot.
Can I do one clarification
Yeah,
though?
please.
Okay, so activation energy is about kinetics. Kinetics is the study of time. Thermodynamics is the study of energy. And so when we're talking about exo and endothermic, that's talking about the energy transitions. You're going from high energy to low energy, exo, low energy to high energy, endo. That's thermodynamics. And so that's, will it happen? Is it possible for this reaction to occur? Kinetics is how long. And so activation energy is really a measurement of how long something's going to take. So you need enough energy, and it can guide us to figure out rate constants. And so often people combine these two things, but it's will it happen is thermo. At all. And then how long. And so from a standpoint of like going in the lab, I care about kinetics. I want to know how long my reaction is going to take. Because can I go home? Do I have to stay here all night? Like, so kinetics actually matters. So that's why people care about activation energy.
So you want the experiment to be done before you go to sleep.
Yes. Or
before you die.
Right. Or you can set it up and then go home and work it up in the morning. Right. That's best case scenario.
Okay. All right. This is Lawrence Harris. And Lawrence says, good day, gentlemen and gentle lady. What is happening when you raise sugars to the candy temperature? It starts as a liquid, becomes a soft candy, but if you keep raising the temperature, it will eventually become hard.
What's up with that?
What is going on there? And by the way, worst candy ever.
And also, there it is, a liquid, and you think, oh, let me just taste that.
Oh,
it's like,
look at
that's way
that.
hotter than boiling water.
Look at that. I burn not only my finger, I don't have a finger, I have no tongue. I hate candy now. This is just a disaster.
I hate chemistry.
This is terrible.
So we talked earlier about dissolving salt in water,
yes.
And it's a very similar thing. So you're going to dissolve sugar in water. They're going to form intermolecular forces, and so that's going to dissolve the sugar crystals with the water molecules.
Will that also drop the temperature?
In the beginning, yes, but it's not going to be as much because it has a Van Hoff factor of 1. It doesn't break apart.
That's somebody else.
Yes, that's somebody else.
Some other chemist of the past.
And so for the ionic species, when you put them in water, they break apart.
I want a Biebdorf factor.
You nice. I don't have one.
You don't have
I
a
should
factor?
have one. No.
You can't hang unless you have a factor.
I know. All right. Well, next time I'll have one by the time we come back.
All
but
right.
for sugar, you're going to dissolve. In theory, it would decrease your freezing point, but it's not going to be much because it's a covalent species. In the same breath, when you put sugar in water, it's going to increase your boiling point, and so that's why you can get that temperature a little bit hotter because the sugar is there to kind of mess with that. So what's interesting about sugar is that when you heat it up, it's going to dissolve. You're going to increase the solubility, and so
That's true for anything.
For anything,
right.
yeah.
Right.
Well, it's true for salts and solutes. But if you use a gaseous solute, you increase the temperature, it decreases. Yeah, it's the other way.
So if you boiled soda, then the gas just comes out. It doesn't stay dissolved in. Right.
Boom.
Got it. It's
yeah.
the opposite.
It's the opposite, exactly. So when you add sugar in, you're going to heat it up, and then it's going to dissolve. And so that's why you heat it. But it's the cooling process that really dictates whether or not you're going to have like a smooth candy or the hard candy, like rock candy. So if you don't touch it at all, you're going to allow for your system to kind of minimize the entropy, lock into these beautiful cages.
Give it a chance to do it all by itself.
Exactly. Yes. Yeah. Let it settle. And then you'll get these gorgeous rocks on, and you probably have to put like a stick in there, but you'll get those rock candies that are typical of rock candy. But if you mess with it while it's cooling down, if you stir it, if you kind of shake it up a little bit, you can't form those gorgeous crystals. And so you're not going to get rock candy. You're going to get something closer to like fudge. And so it's a lot smoother. And so it's really, in my opinion, all the cooling process and like how are you allowing those crystals to form?
So it's not how you heat it, it's how you cool it.
That's my understanding.
No, that makes sense. My mom used to make candied sweet potatoes. And the way you start the candy process is, and they call it candy, it wasn't actual candy. It's a sweet potato with a sugar coating. But the way you start it is you just take regular table sugar, you put it in a pan, and under a low but intense enough to melt heat, you bring the sugar slowly up to a temperature
Just pure sugar.
Just pure sugar.
No water, anything.
And no water, nothing. But you can't do it too fast because you'll just burn the sugar.
Burn the sugar.
But what happens is the sugar very slowly, as you watch it, you can see it from the bottom, as wherever the contact with the pan is, it just kind of splays out and becomes brown and caramel-like, and it slowly becomes this kind of gooey, like caramel-like sugar. And then, depending on how you cool it, or you do something to it, you stir it, whatever, but then it becomes like a syrupy fudge. And then when it cools, it just becomes like a little like caramel coating over top of the sweet potato.
So your kitchen was a chemistry lab.
Oh, definitely. Let me tell you something. It was one of my favorite things to watch.
So kitchens are the thing.
Yes, every kitchen is a chemistry lab. Thank you for making my point.
Yes. Because it's just, I need some of this and some of that.
Yes, you're
and
cooking.
it's all lined up for you and all the cabinets.
Yeah. I didn't think of it until now, but that's absolutely
Especially baking. Baking for sure is chemistry. Cooking is also, but there's a time component. You can have fun with it. Baking is precise.
Very
you need
precise.
to be exact. And
Right.
Yeah. So
No,
the ratio's
but
important.
if you take albumin from an egg, which is otherwise transparent, then you heat it, not many things will you heat do they then become solid, but the colorless part of it becomes solid.
Yeah.
That's kind of weird.
Right.
Well, it's all about those proteins, right? I think they're opening up, and then they
Okay.
can form bonds between each other.
Right.
So I've seen this done, and I thought it was magic, where if you take sweetened condensed milk, okay, and you boil the can closed for like an hour, then pressure builds up in the can, and then you come back and then you open it, and it's like caramel pours out.
Wow. Okay.
You haven't done that?
I have not done that.
Oh my gosh!
I'll try that.
I thought it was the experiment. The chemist hasn't done yet.
No.
So sweetened condensed milk.
Okay.
Okay.
So it must have a really high sugar content.
Yeah, because
right?
sweetened and it's
Yeah,
condensed.
and it's condensed.
Yeah, you use it for things like key lime pies
Yeah.
and
All
things
kinds of baking.
Like this baking.
Like
Yeah,
super
oh,
sweet
yeah,
baking
yeah.
stuff.
where you need the milk, but you don't need as much milk.
Sure.
So you'd have a reduced milk.
It just must have a lot of sugar, though, if it's able to turn it into essentially
Yeah, but
the
with the
liquid
milk.
candy.
With the
yeah.
milk, it's not just
So it's a fat piece, so that must give it like the creaminess or
yeah.
something.
Oh my
Ooh,
gosh.
fancy.
When I saw that done and they opened the can and poured, I was like, no, wait a minute now. Come on now. I thought they were.
I don't know. I think that's how they make dulce de leche, but
That's what I'm saying.
Yeah, I'm pretty
was
sure
very
that's
dulce
how
de
they-
leche-y.
Yeah.
Yeah.
It's pretty cool.
That sounds
Okay.
good.
All right, here we go. This is Caleb Lillard, or Lillard, if the double L and he's Spanish, who knows?
Caleb surely knows.
Yes,
Okay.
exactly.
Go ahead.
Caleb says, "Good day. This is Caleb Lillard from Dallas, Texas. Considering the increasing attention being given to the awareness of PFAS chemicals and how prevalent they are in everyone's lives, I honestly was just wondering if what is being spread through typical means of communication is more hyperbole, or if it should be associated with the level of gravity with which it has been paired." All right, so anyway, this question goes on, but really what he's saying is this. Are PFAS as dangerous as we think they are?
Are these things that never go away in the environment?
Right,
Yes,
that's the problem.
exactly.
Yes.
I heard about it, but I don't know
For-
anything about it.
They're called forever chemicals. is what
exactly.
they're called.
And what is the acronym for?
So it's per and polyfluoral alkyl substances.
Okay, let's keep it at PFAS.
PFAS, yeah.
Duly abbreviated.
Yes.
Right.
But
PFAS.
the big piece is they have a carbon chain as the backbone, and then they're connected to fluorine. And
Wait a minute, doesn't everything have a carbon chain? in
a
the air?
lot of things, not everything.
Aren't we just carbon chain?
Yes, we are just carbon chains too. But for PFAS, they've got this carbon backbone and they're connected to fluorine, and they're really strong carbon fluorine bonds, really strong. And so that's what make them forever chemicals.
Because they can't be broken down.
Not easily.
Not easily.
Not easily.
Or,
And so
or
if
it
you,
takes a long time to
Wait,
break
so
them
those
down.
chlorofluoro,
carbon
carbons?
CFCs.
That's fluorocarbon, it's in there too.
Chlorofluorocarbon. So that usually is a much smaller molecule. And so it's
Okay.
like my memory is that there's carbon
These are
and
the
then it's
ones that
attached
were
to a couple things.
from the refrigerant.
Right.
That,
It's
The ozone
we're
hole.
killing the
hole.
ozone.
Okay, so I'm confusing the two.
It's okay.
Go ahead.
So, but that's good to clarify the difference. So CFCs are much smaller, but they also are bad for the environment. They're gases. So PFAS here are much bigger molecules. And so if they get into our body, because they're forever molecules and we can't break them down as easily, they stay in
stay.
our body.
Right.
And so that's what's a problem. And
But
this
just
is
to be clear, you have to quantify for me. How big is a big molecule?
well, it ranges, and that's the problem. So there's 15,000 different molecules that can be considered a PFAS. And so that's the problem with this. It's really a generic term.
That's
At the end, we're just PFAS chemicals.
yeah.
it
I'm
sounds
going to
like.
say that's not hyperbole.
It's not
That
hyperbole.
is scary as hell.
Yes, and it's particularly troubling for women. We know that it causes fertility issues. We know that in young women, so teenagers or girls who have yet to go through puberty, it is causing a delay in puberty. So we're seeing that issue coming up.
Wait, why can't we just poop it out?
Well, I think it's because it sticks with inside of our body. It must be forming some kind of like intermolecular force with the inside of our body, and so it's strong enough. Because I wouldn't be surprised for I'm speculating, but I wouldn't be surprised for fluorine to easily form some kind of intermolecular force with something in our body. They have 3 lone pairs on them, so it's really
Through
easy.
the digestive tract, it
Something,
gets
yeah,
absorbed in.
anywhere.
Okay, so
Yeah.
is it hyperbole? And where did wait, back up. Where do these come from?
They are generated. We make them a lot of times. Yeah, I would say actually, I think all the times we
On
make them.
purpose?
Yeah.
For what?
Plastics, basically. Linings inside of bottles,
So we're killing ourselves.
basically.
That wouldn't be the first
It's-
time this has been a thing.
We have a pattern.
We have a pattern. We're sensing the pattern. All right. So it's in the environment.
It's in the
We
environment.
ingest it, and they never leave our bodies.
In theory, right? And I'm sure the smaller ones probably you can leave, but if the bigger they are, the more likely it is for them to form a bond inside of our bodies. And so it's problematic. Am I going to try to eat PFAS? No. Am I going to try to avoid it? Yes. And so I don't think it's hyperbole. I think we really should avoid it.
Okay.
Wow.
Well, good question.
And if it's plastics and linings, there's no FDA label for PFAS, so you have to just read articles that highlight it, right? So what's the biggest source of PFAS into our system?
Well, I don't want to point fingers, but a lot of times it has to do with chemical waste, right? And if we're not disposing it properly, then it can get into our water system.
supply.
Why don't you want to point fingers?
Well, I mean, I should point fingers.
Because those companies are chemical companies.
Yes.
I'm just saying.
Because they'll point their finger back at you.
And I want to get hired. I'd rather be on their side and then advocate for good science and maybe
Right.
help them fix the
Got
problem.
it.
So that I want to be a chemical
Rather than play a
advocate.
blame game.
Correct. Yes.
Right,
I want to
right.
help.
There's two different tactics.
Correct.
Yes.
Yes.
Yes. All right.
All right. Okay.
Well, thank you for that.
That's a good question.
Yeah, so this is Alan Rayer. Alan says, hello, Dr. Kate. Privileged to follow you on Instagram.
Oh, thank you.
There you go.
It's Alan from Lithuania here. What gives colors to the elements? Why does the color change in an element based on molecular bonds?
Ooh, I love
Okay.
that.
So couple different answers here. It depends on the context of the question and what we're specifically looking at. So if we're looking at metals, just a generic metal in the neutral state, when we have an excitation, our electrons are going to move. They're going to go up in a level. Think stairs. So they're quantized energy levels. So the electron will literally drink a Red Bull and then run up a bunch of stairs. That process is normal. But when they fall down the stairs, just like if we as humans fall down the stairs, we're going to scream and release energy. Electrons do the same thing. So as they fall down these steps, these quantized energy levels, they release energy in the form of visible light. And so if you have a big gap, you're going to see a high energy light, blues and
But
purples.
is that what he's asking? Was it more simple, just different things have different colors? So
But that's why,
rather
though.
than glowing, that's a glowing metal, right?
It's an excited metal giving off light, right?
Like
well,
tungsten.
Okay, like okay, but yeah.
Well, that's thermal, though.
That's thermal,
rather
yeah.
than
That's different. Yeah. So, okay,
electronic.
but like, what about a quantum dot? So, a quantum dot is something where if it's really small, like 2 nanometers, we're going to have a color of blue being emitted. But if it's a little bit bigger, with 6 nanometers, not that much bigger, we'll see
It'd
a
be a
color
red.
of red.
Yeah.
Yeah, exactly.
Oh.
And so
That's the
there.
wavelength of the light
That is giving
that
off.
would
That's
be-
really wild.
So
Get out of here.
yeah, that's how I think about it. Is how just like it's emitting light, and that's the color we see. So that's the context I
So
usually.
what about all the things that are colorless?
Oh well, they are not emitting
Or just
something.
white, like salt and sugar
Sure.
and flour and, there's so many things that just have no color.
Well,
The kitchen would be so much more interesting.
no color that our human eyes can see. We only see the visible spectrum, so we can see from 400 to 700 nanometers.
It's physiology.
But if it's outside of that,
With
we
your
don't see
stupid
it.
human eyes. Your big dumb human eyes
dumb-
can't see
dumbass.
anything.
way she said it. Damn.
It's true.
She acted like she could see outside that spectrum and the rest of us can't.
I can't.
All right, keep going, Chuck.
All right, this is Daniel Gilligan. Daniel says, greetings, friends. Daniel here from Tasmania, Australia. Okay,
What was that?
that was my Tasmanian devil.
Really, is that even allowed anymore?
He says, how come water isn't the most flammable thing in the world, especially salt water? As separate elements, oxygen, hydrogen, and sodium are all very spicy when it comes to being flammable
Oh,
or
yeah.
dangerous.
Wait, so let's start this off. What happens if I put a hunk of sodium in water?
Oh, you're going to see hydrogen gas is going to be evolved, which is extraordinarily flammable. It's an exothermic reaction, so usually it will ignite and you'll see a flame. A boom.
That's the chemist's way to say
Saying
it'll
it's
blow
gonna
up.
blow
Boom. Yes.
Lot of yeah.
That's sodium, and sodium is in sodium chloride, salt. And then we know
But they're different. Those are different. Sodium that you throw into the water is a chunk of metal, and that's an oxidation state of 0.
Okay.
But sodium chloride has an oxidation state of +1. And so the short answer to the question is, where are the electrons next to these atoms? And so it's how they're sharing them or they're transferring the electrons is going to dictate how they're going to behave.
So
This is unbelievable stuff.
wait,
It's
wait,
like-
so the molecule, you cannot infer the property of the molecule from the properties of the atoms that go into it.
You can if it has the same, if you're comparing like apples to apples. So if you're comparing CO2 versus SiO2,
That's one way.
that's one way you
Okay.
can compare it.
However, I'm saying, like the questioner said, we know hydrogen is flammable.
Right.
We know oxygen
Oxygen is
feeds flames.
flames.
You put them together and it extinguishes flames.
Yes.
That's weird.
It is weird, but they're so different though, because hydrogen is H2. It's two hydrogens bond together, so they're sharing 2 electrons. You've got oxygen has a double bond between it, so they're sharing 4 electrons. That's a really strong bond. And then water has 1 oxygen and 2 hydrogens. Those hydrogens are not next to each other. The oxygen's
right,
in the
they're
middle.
separated.
Yeah. And oxygen is the second most electronegative atom that we know about, meaning it pulls the electrons from its species. So in hydrogen, the electrons are being evenly shared. In water, most of the electrons are completely up on the oxygen. And so it's all about where the electrons are in the reactivity.
So oxygen steals electrons
Every time.
like no matter. It's just
Like it's nobody's
basically it's a thief. Like don't bring your girl around oxygen.
That's the perfect
'Cause
analogy.
Don't bring your girl around oxygen. We know the deal. Oxygen is like Michael B. Jordan. Your woman is leaving with him tonight.
Yes. That's exactly it.
Okay.
I'm going to use that in my classroom, by the way.
Okay.
Wow.
So, Kate.
Yeah.
I understand that you have a podcast.
I do.
An NPR podcast.
Yes, Seeking a Scientist. We
That
just
means
dropped.
all the right investments and anything are going into it.
Yes, exactly. So we just dropped season 2, and our first episode of season 2 was about being in space. It was the DART mission. We interviewed Nancy Chabot.
Double asteroid redirect test.
Yes, exactly. And so
Yes.
we go through the entire process from the beginning of the creation of the experiment all the way to now what's happening and what their future missions are planned. It's awesome.
So these are scientists active in something that you might be interested in as a listener.
Yes, and I would someday love to have a chemist on there, but yet it's been completely other than chemistry. Like we're talking to someone who studies dogs and
It's
how you
not ask
pick.
a chemist, it's just ask a scientist.
We're
which could
seeking
come
a
from
scientist.
from any field.
Exactly. We've got this one woman who's doing research on puppies to figure out how you can determine what is the best service dog. Like that's her research, is figuring out how to predict that. So we interview her, and so that's coming up in a couple
The
weeks.
answer is it will not make a difference because in 10 years, all service dogs will be autonomous robots that actually just guide you.
Oh, I love the golden retrievers. I want them to stick around.
Yeah, guess what? Robots don't poop.
Not yet.
Not yet. So it's filmed in your hometown, where you are in Austin?
Yeah, I film out of Austin, and we interview scientists from all across the planet.
Wow.
Okay, so they'll virtually.
Virtually, yeah, it's all virtually, but the host city is actually Kansas City, so I got to give a shout out to KCUR.
Okay.
KCUR, okay. As in the public station
station.
model.
Correct.
It's distributed. It's
Yep.
not one central creating point. And so they create it, and then it's shared with other
Correct.
stations.
Yep.
All right. Well, Kate, it's been delightful. Finally, we met over the internet, but not in person. Thanks for coming by.
Thank you for having me.
And
It's so
sharing your
wonderful.
media calendar with us here.
Thank you.
All right, Chuck, always good to have you, man.
Always a pleasure.
All right. In conversation with a chemist, which doesn't happen to me often, I'm just reminded how much of this world is empowered by chemists. What they have done for us has transformed our lives in every measurable way. Yet, at the end, it doesn't say, by the time you use your cold pack, when you're done and your knee is a little better from this endothermic reaction that a chemist put in here, thank your nearby chemist. No, there's no such instructions there. We just do it and take it all for granted. I should have a conversation with a chemist more often so that I take less of what happens around me for granted. If you don't get to have a conversation with a chemist, next time you make anything in your kitchen, just sit and reflect on the fact that none of that would happen without chemistry. And that's a cosmic perspective, not only on the universe, but on your everyday life. Keep looking up. This is StarTalk. This is a Things You Thought You Knew edition. And that means it's just going to be me and Chuck for this whole episode. Can you handle it, Chuck?
No. I'm overwhelmed. Because I already know that I don't know. See?
Okay.
There's no thinking. There's no thinking that I know.
Okay, so we're going to, let's first take on the topic that's so simple. Why do things break when they fall? What do you think of that?
See, but this is what I've learned from Things You Thought You Knew. There are times when, in the past, at full disclosure, where you have said, so we're going to talk about floating, things that float. And in my head, I will say, not audibly, of course, but I will say, Neil has lost his damn mind. He wants to sit here and waste people time talking about why something might float. And I'm like, well, all right, bro, whatever. Let's get into it. And then we start talking about it. And by the time it's over, I'm like, oh my God.
Okay.
So
here you go.
Here we go.
Let's do it. Okay.
yeah, why things break when they fall.
Yeah. So maybe it's obvious to some people, but just I thought I would tease out the physics of what's going on. Okay. All right.
Okay.
So you have a plate that is up on a shelf.
Okay.
Right? It's a breakable plate.
All right.
And somebody shoves the plate, it falls, it hits the ground and breaks.
It's a cat. A cat did that.
A cat did that, for sure.
It's always a cat.
For sure.
Right.
Okay. One of my favorite memes, was it a meme where they said, we know the earth isn't flat because otherwise cats would have pushed everything off of it by now.
I never saw that, but that's
good.
Hilarious.
That's a really good evidence
yes.
that earth is not flat. All right. So the plate is in front of you. You actually have to commit some kind of violence on the plate to do it. Okay. So what you have to do is ask how much energy is holding this plate together.
Okay.
All right. So you go down to the molecular level and see how strongly the molecules are bound to each other. Okay. So in a crystal, for example, they're pretty strongly bound together. So if you try to break a crystal, it's hard. It takes more energy to break a crystal. All right. And so, but it's a fragile sort of dinner plate. All right. Not a plastic plate, but just one that can break. You actually have to put energy into it, and the plate will not break unless the energy you put into it is greater than the binding energy of the molecules holding the plate together.
Okay.
Okay?
And that makes sense.
That's simple. Doesn't that make sense? It
Yes.
makes complete sense.
What doesn't make sense right now is binding energy.
Okay, so well, I thought those two words mean exactly what you think they mean in that sentence. So the two molecules that are adjacent to each other, all right? Now, why doesn't the plate just separate all by itself?
All by itself.
Yeah, something is holding the molecules together. Okay? It could be any one of a number of kinds of forces doing it, but nonetheless, they're attached to each other. And if you introduce energy that's greater than the energy that's holding it together, you will break that bond.
Gotcha.
Okay. So that's how anything breaks, basically.
Right.
But
yeah.
we're happy to use dinner plates for this example. All right. So if it's just sitting there in front of you, and if you pound on it, you'll break it. All right. So you had to put energy in it. But wait a minute. The plate that's sitting on a shelf that the cat pushed off, you're not pounding on it. You didn't pound on the plate. Nothing touched that plate. Okay? Did the cat break the plate? No. The cat just showed the plate the edge of the shelf.
And even if the cat broke the plate, you know cats, they'd have been like, I ain't break your plate. I don't even know who you're looking at. Why are you even looking over here? First of all, why are you in my house right now? That's what I'm trying to figure out. Who the hell are you? And why do you show up every day? How'd you get a key? Is what I want to know. How did you get a key to this house?
Well, can I get back to breaking plates, please?
Anyway, so the cat didn't do anything to the plate.
The cat didn't physically break the plate.
Right.
Okay? So what broke the plate? This is the question. You know that if you take a hammer and hit it to a plate, it'll break. You know if you pound your fist on the plate, it'll break. You know all this. Okay? Why did the plate break when it fell off the shelf?
Because it hit the floor.
Okay. Yes. Okay. Okay. It hit the floor with a certain amount of energy.
Correct. Yeah.
Okay. And the higher the location it falls from, the more energy it's going to have. Does that make sense?
Of course, yeah.
And you know what kind of energy that is? Energy of motion. So we have a word for that.
Kinetic?
Kinetic energy, exactly. So the kinetic energy of the plate that it had the instant before it hit the floor, you have to ask, how much energy is that compared to the binding energy of the plate? Okay. All right.
Right.
So does that exceed the binding energy of the plate? And if it does, the plate will break. Okay. Where did the plate get its kinetic energy from?
Gravity.
Gravity. Okay. All right. But gravity didn't put the plate on the shelf.
Okay.
Who put the plate on the shelf?
Well, I mean, who lives with the cat? Because
That's who put the plate on the shelf.
yeah, because you know.
Okay. So the plate used to be at a low location,
Right.
and somebody walked up to the plate after it was cleaned. It was like the lower shelf of the dishwasher. They picked it up, used their energy to give that plate what's called gravitational potential energy. Okay? And the higher you put the plate on the shelf, the more gravitational potential energy it has. And then the plate just sits there in possession of gravitational potential energy. It just sits there. And if you if the cat pushes the plate off the shelf, the gravitational potential energy swaps and becomes kinetic energy.
Right.
Okay? Until it has no gravitational potential energy left, which is right when it hits the floor, and all that energy becomes kinetic. And this dance between kinetic energy and gravitational potential energy is what goes on in every curve and every turn of a roller coaster. Okay? Other than the first pull up the top,
Right.
okay, where there's like chains and motors, everything else is free fall, basically. You're in free glide. All right? And so that's why when you go up a hill, you slow down. Well, why are you slowing down? Because the gravitational potential energy is taking away your kinetic energy. And once you get to the top, why do you speed up on the way down? Because the kinetic energy is taking away, is being converted from the gravitational potential energy. And your fastest point on an entire roller coaster is going to be where?
The fastest point?
Yes.
You mean where you reach your top speed?
Yes. Where's that going to be?
The bottom of the first drop.
The bottom of the lowest point of the roller coaster is going to be your highest kinetic energy, and your highest potential energy is obvious now. It's going to be whatever is the highest point on the roller coaster. Right. So the roller coasters fully exploit this gravity, kinetic energy, potential energy relationship. Okay, and all I'm saying is, you want to know who broke the plate? You did, because you gave it the energy to break in the first place by ascending it to that shelf.
See, it sounds to me like you've been talking to the cat. Because that's something the cat would say.
I had nothing to do with this.
What you talking about?
Whoever put it here, it's their fault.
All right, I was just introducing you to some gravitational kinetic energy, okay? Getting rid of some potential energy. And by the way, the broom is over there, okay?
Okay, so let's keep going. Okay. Now, suppose the plate fell from an even higher height.
Okay.
All right? It just doesn't break into two. What happens?
Oh, it shatters.
It shatters. Unless there's some other sort of structural aspect of it, like safety glass shatters rather than just breaks into large pieces. That, you know why it's called safety glass? Because the pieces are so small that one piece can't go in and like cut your jugular, right? You'll just be like surface damage to your skin with safety glass. That's why it breaks into very small pieces like instantly. So
it's death by 1,000 shards
instead of one.
Instead of just one big one that cuts you in half.
That pierces your aorta. All I'm saying is that if it's higher, it gains more kinetic energy because you gave it more gravitational potential energy. And by the time it hits the ground, it has much more energy to break the plate with. So it doesn't just break it in 3 places, it'll break it in 100 places. Right. There it is.
Nice.
So that's why things break when they fall.
I have to say, once again, I'm impressed. Got to tell you right now, I thought at the end of this talk that I was going to feel like the cat. Like, what the hell?
Wait. So, and just to be clear, you could make something. If you wanted to say, I want to make a plate that doesn't break.
Right.
All right. So you make sure the binding energy between the molecules of the plate is greater than the energy that it would be given by the cat if it fell off a very high shelf in your home. And so it's basically unbreakable for most things that would happen in your home. And so you could calculate what that energy is and find a material substance for which that's the case. So that's where you get break resistant. So
I was going to say, yeah.
Break resistant stemware for clumsy wine drinkers.
Yes.
So the material substance of it has higher resistance it requires more energy to break it than what is normal and typical for a delicate wine stem.
I had a job where I had to demonstrate something that was billed as unbreakable at the time.
Mm-hmm.
And when you were supposed to demonstrate it within reason, okay, I took it and slammed it down and it exploded. And I then said to the people, maybe it is break resistant.
That's right. And that was your first and last day on that job, right?
Oh, without a doubt. Are you kidding me?
All right, so there you go, Chuck.
Listen, here's the one thing I know now. The earth is not flat.
Thank you. If that's all, okay, if that's your only takeaway, that's a start. That's a start. All right, we'll be right back. Chuck, ready for another one?
Oh, yes.
Okay, this is the topic of white noise.
You know...
No, don't go there. Just stop.
I'm just saying.
Chuck.
Since January 6th, now that we brought it up.
No, I did not bring it up.
Now that we brought it up, I got it. Just, since January 6th has happened, while we're on the subject.
White noise was long defined before the chaos at the Capitol. Okay. All right. So, white noise is what is described as a combination of sound frequencies that ends up just sounding like a hiss. It's a hiss. Okay.
Right.
And so, what's going on there?
As opposed to black noise, which is shut them damn kids up. That's black noise. Y'all know I'm down here trying to watch my stories? The hell is wrong with you? That is black noise. That is black noise.
Thank you, Chuck. We'll introduce that to the annals of physics.
Right.
All right.
Okay. All right.
Like I said,
enough silliness.
So here it is. So what it is, it's a mixture of all frequencies of sound.
Oh, wow.
All at once. Okay. All audible frequencies of sound. Okay. You could add in others, but it won't make any difference because you can't hear them. Okay. So white noise is low frequency, middle frequency, high frequency. And there are different ways you can do it because high frequency sound at the same amplitude actually carries more energy. So you might sort of adjust it so that you have the same amount of energy, sound energy in each sort of frequency band. All right.
Okay.
So there are different ways to define it. The point I'm making is all frequencies of sound are sampled, and what that sounds like to you is a hiss. It's like okay.
Right.
So they say
it's so unfortunate now that we live in an age of digital streaming and cable television, because kids will never get to know what white noise sounds like on their television.
The hiss when you're between channels, when TVs were actually grabbing radio frequencies from the air,
yes.
Right, with the antennas, right. If you were between channels, or if the channel went off the air, you would see static. on the screen, and that would be the sound of white noise.
Yes.
By the way, some fraction, a few percent of the hiss that is on that screen is the cosmic microwave background.
Oh, that's hot. As opposed to the world where Carol Ann was taken in Poltergeist.
Oh, okay. Right. I'm not authorized to speak further on places such as that. So that's what it would look like if you made sort of image on a screen. But that would be, by the way, that would be electromagnetic noise. Ooh. So that's not audio. Yes, they turned a radio signal into an acoustic signal.
Right.
And that acoustic signal comes across as a hiss, as a white noise. All right.
That's so cool. That's so cool.
Just to be clear about that. So now you have to ask, why is it called white? So here's where it comes from. If Isaac Newton, one day, the sun is shining through his window, and he closes his curtains, or he cuts a hole in the wall. I forgot which. Might have done both. And just one narrow beam of sunlight comes through the wall.
Okay.
Then he takes a prism, a 60-60-60 equilateral prism. Okay. And he puts the sunlight through the prism, and on the other side of the prism comes the rainbow. Right. The colors: red, orange, yellow, green, blue, violet. Okay. But he had a mystical fascination with the number 7, and those 6 colors don't sum to 7. So he added one. Which color did he add?
Indigo?
Indigo, of course. So we have red, orange, yellow, green, blue, indigo, violet. All right. And that spells everybody's friend, Roy G. Biv. Okay. We all love Roy G. Biv. All right.
Yes.
So there are his
almost as much as Belle Biv DeVoe.
That was good. Belle Biv DeVoe only knew. Had a cousin called Roy G. Biv.
If only they knew.
So anyhow, so it has all the colors there. Okay.
Right.
So the question is, did the prism create these colors? Because the white light is no longer visible.
Right.
And this is what everyone presumed. Of course it created the colors. Because if they were there before it entered the prism, you would see them.
We see them.
Of course. So then he said, well, what'll happen if I take another prism, put these colors back through, let's see what then comes out the other side. And you know what came out the other side? White light. And so Newton was very clever, not just because he was smart, but clever in his experiments and what questions to ask and how to adjust the experiment to test for things where it could be one thing or another, but let's readjust the test to distinguish what explanation might account for it. Oh. In so doing, he showed that white light from the sun is composed of equal amounts of all the colors in the rainbow, in the spectrum. And by the way, rainbows, people said, oh, the raindrops are making the colors, not the sun. It's in the sunlight. This is freaky. How could color be in white light? What the hell is going on? Okay, well, you got to get into the physiology of the retina and the brain and all of that. The point is...
your eyes are racist. That is how all the light is white. All the colors come in to your racist eyes, and all they see is white.
I'm afraid I have to just say that is the physics to the truth. There it is. That's the physics of it. So the point is, if you combine all those frequencies of light, the red, the orange, the yellow, the green, the blue, the violet, and combine them all, and you have equal amounts of them all, you get white. So this word in that context was then borrowed by the sound people. If you put equal frequencies of sound, okay, it's not a thing, it's just this noise, we shall call it white noise. Even though the sound, unless you're synesthetic, where you have cross-wired senses, The sound is not a color, all right? But we say it's white out of homage to Newton and the colors of the spectrum and the fact that you put all these colors, these different frequencies together, and you get the color white. So that hiss is white noise for that reason.
Yeah, and it's funny because it is. I understand the borrowing of the term. That makes sense, just because it's the same picture of what.
Yeah. Plus, you're using frequencies.
You're using
frequencies, right?
So it's sound waves, light waves, the whole deal. Frequencies.
Exactly.
So that all makes sense. But the term doesn't really fit for like you say, unless you're you have synesthesia. It doesn't fit. We need a better term for white noise, is what I'm saying. Okay.
Okay. So the point is, noise can be any combination of those frequencies, but when it's equal across the board, only then is it white noise.
Why can't it be equality noise? Okay.
DEI noise, diversity, equity, inclusion.
There you go. Diversity, equity, and inclusive noise.
That's what it's doing. It's including
DEI.
everybody.
And we can call it day noise, DEI noise. Right now, let me tell you something. Right now, there are some Fox News viewers that are watching us right now, and their heads are exploding. Their heads are exploding right now. No. Bill Maher just threw up right now.
Yeah, because he's anti-woke.
Yes, he's so anti-woke. But no, it makes perfect sense, honestly, to borrow that picture.
But it's a very specific kind of noise.
It really is.
Otherwise, it's not white noise. For example, if you had more red in your spectrum than blue, and you mix them together, the object will have a red hue to it. Right. Okay? Yeah. And if you have more blue in the mixture rather than red, it would have a blue hue to it. In fact, red stars and blue stars in the sky are exactly that. They're giving you all frequencies, but they lean towards that side of the spectrum that has those colors. So I think it's okay to borrow terms that make sense in other contexts. I don't have a problem with that.
Yeah, it paints the picture. I mean, the problem is not too many people know the Newton story. That's my point. Is that it makes perfect sense once you explain the Newton story. I'm like, oh my God, that's awesome. I get it now. White noise.
And if your acoustic noise is clankety clanking, or if you can find any signal within that noise, it's not white noise.
It's not white, right? Exactly.
Right.
Yeah.
Right.
Yeah. Oh, that's very cool though.
Okay, I thought I just set the record straight there.
Yeah.
John?
Once again, I'm impressed that you took, something totally stupid, made it super interesting and informative. I'm tell you something. I don't know how many times you can pull this trick.
Plus, I don't want to hear later on that you come out with an album, Black Noise.
Oh my God, that should be my next album.
Chuck's
Black Noise.
That is good. That's good.
That's a good name for an album. That's all
that could work. That could work. Black Noise.
Black Noise.
You heard of white noise? Here's some black noise.
There you go. Shut the hell up. All right?
Don't make me put my foot up your ass.
There you go. That's more black noise.
All right. We got to end.
And by the way, let me just say this.
What?
Black noise and white noise make perfect sense together. Okay? It's just like, what the hell is going on? How many times I'm going to tell you? Shh. Shh. Man, shut the hell up. Black and white noise.
They belong together.
Oh, man.
So, Chuck, you ready for another segment?
Absolutely.
Okay, so let's take a quick break. And when we come back, the third and final segment of Things You Thought You Knew. We're back. Star Talk. Things You Thought You Knew edition. These are fun, Chuck. I like doing these.
Love it.
I prefer having a guest because I don't like being the center of anything. But I'd rather showcase the expertise of others. But there's these dangling holes in all of what people know and think is going on in the universe, and I just got to patch them up.
I like it. I think it's more fun when it's just us.
Oh, okay.
Yeah. I mean, I like guests too, but this is nice.
Okay. Actually, I'm lazy, and I'd rather like the guests do all the work, right? Because it's their expertise we're tapping.
Right.
But there are certain things in the world that are incomplete in people's awareness of how things work, and so.
Well, that's the fun of this, is that it goes to a place where you would not logically progress.
Yeah, exactly. There's no step right before it to say, let me go there.
Yeah,
right. Because
exactly.
there's too many lanes and routes and off ramps around it. Okay. And so we'll stand right in the middle of the road.
Excellent.
All right. Okay, so here it is. The topic, things to do with wormholes.
Uh-oh. Watch out.
I just thought,
I don't know, man. I don't know if we should be doing this.
People are not imaginative enough.
That's my point. Why are we giving people?
Let me explain.
No, scientific sci-fi writers right now are watching this here.
Yes.
And going, bro, get a pen.
Yes.
Neil deGrasse Tyson is about to hook us up with some killer ideas on what to do with wormholes.
Do it.
My point is, we should be getting paid for this. This is valuable.
All right, so here goes. So let me remind people what a wormhole is.
Yes.
All right, so we have the sort of the fabric of the space-time continuum. Mm-hmm. All right, so it's not just that space is out there. Space is intricately configured with time. And how do you know this? Because we did this exercise before. I think we did space-time in another show. We did an explainer on that, where I ask you, I say, Chuck, let's have lunch. Let's have lunch tomorrow. Okay, right. Let's have lunch tomorrow at 12 noon.
Okay, and then of course I will say, "Are you buying?"
Okay, no, that's not what I thought.
Of course, it's where you want to have lunch. Well,
yeah. So the question is where. All right. So I set up a time, and you knew that was incomplete.
Right.
And we have to complete the engagement by establishing a location.
Right.
So I gave you a time, tomorrow, 12 noon, and you're going to say where. All right. And I might say you pick whatever, but we need a where. Otherwise, it doesn't work. Mm-hmm. All right. I could be in a place at a different time, or at the same time at a different place, but we have to be in the same place and the same time in order to meet. Okay?
Right.
And on the same token, I can say, oh, I'll meet you at Gabriel's for lunch. Okay? And then you say, what time? All right? So, space-time are forever conjoined for this fact. Okay? Mm-hmm. And other reasons, but that's the terrestrial one that is closest to how we think about the world. All right. This fabric can be distorted in such a way that you can change the distance, the space-time distance between two locations.
Okay.
All right. And one way to imagine that is imagine all of our universe is just on a flat sheet of paper, mm-hmm. and you're on one edge of the paper, and I want to get to the other edge, and I'll take out light years of time, however long that takes. Okay.
Right.
I mean, it's light years distance, so I take many years traveling at the speed of light. But if I take the space and warp it, curve it back on itself, mm-hmm. now your location is very close to me. If I could somehow punch through the fabric of space and time and reach your location.
That's the warp drive right there.
Yeah, well, so the warp drive would accomplish that by other means, right. But it is nonetheless warping the fabric of space.
This fabric of space.
Making something that would otherwise be longer, a shorter distance, and thereby transcending the speed of light to do so. You're no longer limited by the speed of light. The diameter of our galaxy is 100,000 light years. You can't travel across it unless you during the TV commercial, unless you figured out a way to warp space and time. Okay, so in that warp, in principle, on paper, you can have a hole that you pass through and just come out the other side. And you're in another place, and if you did it right, you can show up at another time, but let's just make your timeline continuous with yourself. So you go right through and you come out the other side, bada bing, there you are. That's the most classical invocation of a wormhole. Okay? And by the way, in spite of what Hollywood shows, that when you go through wormholes, it's like you go through the water slide at the water park. No, that's not how, it's just, you just step through.
Right.
And you're there, right? This is accurately captured in Doctor Strange, all right, where he opens a portal. Do they call them wormholes?
No, they don't. They call them portals.
Yeah, just a portal, and that's a wormhole. But in Rick and Morty, they do exactly the same thing, and they're wormholes. They know this, okay? And the difference, of course, is that in Rick and Morty, they're using real science to make their wormholes, whereas Doctor Strange is using magic.
Magic.
Yeah. And you gotta do your fingers in a way and go in a circle, and then the little sparklies on the edge of it too. Yeah. Right.
And there's definitely weird-looking ideograms that they somehow have power. And,
Okay, so things to do with wormholes. All right. Yes, you can move through space and time, just as has been portrayed in the film. But let's get a little more practical. Okay, so the movie Monsters, Inc. was all about wormholes. Did you see Monsters, Inc.? You have kids. You saw Monsters, Inc.?
I did. Several times I've seen that.
Okay, the doors.
Oh, yeah, I see what you're saying.
They're manufacturing doors that the monsters take home, and then they open the door. That is the door of the closet of the kid they have to scare that night.
That's right.
Okay, and there's a big chase scene where they're going in and out of doors in the factory, and they show up in Paris, and they show up in 20 different places with every door they pass through. Those are wormholes.
So instead of a transporter, which molecularly decomposes...
I'm getting there. You were exactly right. Chuck, that's my next thing. So my point is, if you just walk through a door, you walk through a door.
Right.
Okay, that's the wormhole. And while they never said it in Monsters, Inc., which is a Disney Pixar animated feature, very cleverly done, and they're funny. They didn't say it, but those are wormholes. Period.
Right.
Okay. Right. Without the histrionics of a Doctor Strange and without the madness of Rick and Morty, they're wormholes. Okay. Well, if you have wormholes and you can warp space in that way, then the transporter in Star Trek, which dematerializes you, beams your energy at the speed of light to a location, and then you get rematerialized, would be completely unnecessary.
Yeah, exactly.
You just pop the hatch, walk through, and now you're in the other spaceship. Now you're on the planetary surface.
Why'd you have to take me apart?
Exactly.
You completely took me apart, bro.
Completely.
Yeah.
Okay. Plus, there was some episode I was told, maybe in the later series, because I'm less complete in the later series, that there's some fraction of your molecules that are not transported
reconstituted,
accurately. Yeah, there's copying errors.
Yeah, that's why they have the buffer. It's called the transporter buffer system. Because of that, it compensates for that, which is why sometimes, which is so lazy, but I love it. It works. It's like somebody gets lost and they're just like, well, what we'll do is we'll use the transporter buffer to take all of their molecular imprint, and then we'll just bring the person back.
Oh, okay. Yeah. So they don't really die in a pile of goo.
Right.
Right. Okay.
Exactly. Yeah.
All right. So what's interesting there is we're in the age of information, which was not so in the 1960s.
Right.
And so they weren't thinking about information in the same way or at all. And so all you really need to do is make an exact copy of all the information that is contained within you, all the neurosynaptic configurations and everything, and then beam the information to another ship and then recreate you there. And then what that means is I can create you in any location and I can create multiple yous.
That's right.
And I mean, why not? They do that with the replicator. All right.
That's right. That's all the replicator does.
That's all it does.
Yeah.
So in principle, if you have a replicator, you don't need a transporter system. Okay. We just have the information of who you are and transport that. But so that's one thing you would do with a wormhole. Okay. So we have monsters scaring children. That's the first application. Second,
I love it.
Because otherwise, how are they going to get in the kid's room? There's no way they can get in.
Exactly.
Another thing is, imagine if the back of your refrigerator were connected to your grocer.
Oh, wow. He'd stock it the same way he stocks the shelves at the grocery store.
At the grocery store. They take a peek. Oh, you're low on lettuce. And the lettuce is turning bad. They'll take out the lettuce, put in a fresh one. And there is no transportation network involved.
Say goodbye, Grubhub.
So Grubhub is a practical wormhole, right? By the way, you know what else a wormhole is? Another is an elevator.
Ooh,
Think
yes.
about it. You walk into a room, the door closes, and then when the door reopens, you're in a completely different time and place.
That's actually kind of, yes, that.
Think about that.
Yeah.
Before electricity and before elevators and before tall buildings, just grab someone off the street and take them into a modern elevator. Okay?
Oh my God. Yeah,
and then the doors, they're on street level or something, and then they push a button, and then they open it up, and then they're 100 stories up, and they'll freak out. How did that happen? The room didn't change. I didn't see anything. There are no windows. What happened? So for me, an elevator is a modern sort of next best thing to a wormhole that you can come up with.
Yeah.
Right? You could be in one room and then take an elevator, and then it's a kitchen and another room, and then it's like a living room or whatever.
Yeah.
And so just the world changes just in a matter of seconds. So what do we have? So we have the elevator is a poor man's wormhole.
Yeah.
We've got scaring children in their closet. We've got the transporter in Star Trek. We've got the back of your refrigerator. And what that ends up doing is completely removing the transportation sector from the world.
I was going to say, what you really do, I'm home for the rest of my life.
I
I don't have to do anything. By the way,
you don't have to go somewhere to obtain something.
Yeah, everything can come right through the hole.
Right through the hole. Correct. And I got one other, I think I've told this many times, but I even laugh every time I retell it, even though it happened to me and it's my joke, right? So is that good or bad, Chuck? Are you allowed to laugh at your own?
Listen, I say whatever works for the person telling the joke.
Whoever.
That's right.
So here I was in the Charlotte airport. And I had to go from a big plane to a little plane. And the carry-on that I had did not have wheels. So I actually had to carry it. And Chuck, it felt like I walked 3 miles. It might have just been a mile, but to go from a big plane to a little plane in that airport, I must have walked the full width of the entire airport campus.
Right.
And I finally get to my destination with the little bitty ass plane. And I said, I got to tweet this. So I tweeted, can't wait for wormholes. That way all airport gates would be adjacent to each other. You just step through and you're there.
Right.
Okay. And then, because I thought that was a nice geeky thing to, tweeting to my geek base, I got out geeked. Okay. I got out geeked. Here it is. One of the responses was, Dr. Tyson, the day we have wormholes, you won't need airports. I said, oh.
That is true. Yes.
Oh.
Yeah, but now you just put every pilot out of work.
I know. Well, this is a readjustment to the economy. Yeah. That's happened many times before. Nobody's making horse-drawn carriages anymore, or buggy whips, or there's whole industries that don't exist.
I don't. They're still making the buggy whips. They're just not for buggies anymore.
Okay. Chuck. They're just called whips. Okay,
yes.
Fine.
Yeah.
Fine. So basically, the entire transportation sector would go out of business basically overnight, and it's a fascinating reality. But plus, you wouldn't need 12-lane highways to go anywhere.
Right.
You want to go to grandma's house for Thanksgiving? Yeah. Just wormhole in. So each home would have like a general purpose wormhole that you dial the coordinates and come through. But your grocer, they'd only have access to your refrigerator, right?
Right.
And
your in-laws would have access to your friend's house. do not come in here. Man, I'm going to tell you something. I don't like the world with just wormholes. That's a little too close.
You could lock them. We'll figure out a way to lock them. It'd be like your front door, okay? You'd hear a knock,
No, but you can never get away from anybody. Think about it. No matter where you are.
You lock them out of your wormhole.
Yeah, but then they call you on your worm phone.
They're like, I'm right here.
Yeah.
I'm right here.
Hey, man, what's going on, man? Where are you? I just went to your house. You're not home. Right?
No, I'm in Bermuda. Okay, I'll meet you there.
Exactly. Oh, yeah, you're Bermuda. That's great. I'll be there in a couple seconds. No, man, this is not cool. You know?
Okay, I didn't think of the downsides of this plan.
Yeah, right.
Okay, somebody's got to like think it through a little further than I have, but just think, or maybe the wormholes are where the previous ports were.
Right.
You had train stations, airports, spaceports. You have a wormhole port, and so you can't just go anywhere at any time. You got to sort of sign up, and
yeah, that's a little better. Yeah, the other way's a little invasive. You can't even
little
pretend
invasive.
like back in the day when people would knock on your door and be like, oh, okay, we're not answering that.
yeah, in the day you couldn't tell them in advance that you were showing up.
Right.
So you had to be ready to greet someone
That's
at
right.
the door.
Somebody-
In fact, the very word caller was someone who knocked on your front door. And that word was adopted into telephones. And so now we think of caller as only with phones.
Right.
But, the gentleman caller on the lady.
I do believe you have a gentleman caller at the door. My good Delilah, you did not tell us.
You got your plantation accent right on cue there. Okay, so Chuck, that's 101 things to do with a wormhole.
That's lovely. I love it.
Just thought I'd tell you about that. And so let's call it quits there. That's been the third of 3 segments of things you thought you knew.
Yeah.
Hope you enjoyed that.
That was fun.
And as always, I'm Neil deGrasse Tyson bidding you to keep looking up.